Hi everyone. In this presentation, I will explain the paper MapReduce Simplified Data Processing on Large Clusters written by Jeffrey Dean and Sanjay Ghemawat at Google in 2004. This paper is one of the most influential works in distributed systems because it's introduced a simple programming model and an implementation that made large-scale data processing significantly easier. In the next few minutes, I will explain the motivation behind MapReduce, the programming model, how the system executes jobs internally, and the key advantages such as fault tolerance and scalability. Finally, I will demonstrate the idea using the classic word count example and summarize the evaluation results reported in the paper. To understand why MapReduce was necessary, we first need to understand the scale of Google's data processing problems. Google constantly needed to process extremely large amounts of raw data, such as crawled web pages, user search queries, web request logs, and large graphs representing links between documents. Many of these tasks are conceptually simple. For example, counting word frequencies, extracting statistics from logs, or building indexing data structures is not difficult on a single machine. However, the challenge is that the input data is so large that it must be processed using hundreds or even thousands of machines in parallel. At this scale, writing distributed programs becomes difficult because the programmer must manually handle many complex issues such as parallelization, data distribution, fault tolerance, and load balancing. The main motivation behind MapReduce was to remove this complexity from application code and instead provide a framework that handles it automatically. The key idea of MapReduce is that many large-scale computations can be expressed using only two operations, map and reduce. Instead of forcing programmers to write low-level distributed code, MapReduce allows the programmer to focus only on the core logic of the computation. The framework then automatically handles the difficult part of distributed execution, such as scheduling tasks across machines, managing communication between machines, handling failures, and scaling the computation to thousands of workers. This is the reason MapReduce was so impactful. It made it possible for programmers with limited distributed systems experience to efficiently use a large cluster. Now let's define the MapReduce programming model. A MapReduce job takes a set of input key value pairs and produces a set of output key value pairs. The user writes two functions. First, the map function takes an input pair, which we can represent as K1, and V1 produces a list of intermediate key value pairs represented as key K2 and V2. Second, the reduce function takes an intermediate key K2 and the list of all values associated with that key and merges or aggregates those values to produce the output. A critical point here is that the framework groups all intermediate values that share the same key before calling reduce. So the programmer only defines the transformation and aggregation logic, and MapReduce handles the grouping and distribution automatically. Now that we understand the programming model, we can look at the system architecture that makes MapReduce work at scale. MapReduce uses a master worker architecture. There is one master node and many worker nodes. The input data is split into multiple pieces, and different map workers process different splits in parallel. Each map worker produces intermediate key value pairs, and the most important part happens next. The intermediate data is shuffled from the map phase to the reduce phase. Reduce workers fetch intermediate data produced by all map workers, group it by key, and then apply the reduce function. Finally, each reduce worker writes its output to a separate output file. So, overall, the computation follows a pipeline. Input is processed by map workers, intermediate data is shuffled and grouped, and then reduced workers produce the final result. This slide summarizes the complete execution algorithm in 7 steps. First, the input is split into M pieces, so the job contains M map tasks. Second, the master assigns map tasks to available workers. Third, map workers process their input split and generate intermediate key value pairs. Fourth, intermediate data is partitioned into R buckets, where R is the number of reduced tasks. This is usually done using a hash-based partitioning function. Fifth, reduced workers fetch intermediate data from map workers and sort it by key. Sorting is required so that all values belonging to the same key become grouped together. 6. Reduce workers merge the values for each key and write output. And finally, once all tasks complete, the job finishes and the output consists of our file. This process is the core of MapReduce. It automatically parallelizes computation by splitting input into many tasks and coordinating them through a single master. One of the most important contributions of MapReduce is fault tolerance. In a cluster with thousands of machines, failures are not rare events. They are expected and normal. MapReduce handles this by having the master periodically ping all workers. If a worker does not respond, the master marks it as failed. If a map worker fails, its completed map tasks are re-executed. This is necessary because intermediate output from map tasks is stored on the local disk of the worker. And if the machine fails, that data becomes inaccessible. If a reduced worker fails while running, the reduced task is also re-executed. However, reduced output that has already been completed does not need to be re-executed because it is stored in a global distributed file system rather than only on a local disk. The system also uses atomic commits. Tasks write output to temporary files and then atomically rename them when complete. This ensures that the final output is consistent and corresponds to correct execution, even if tasks are rerun due to failures. So overall, MapReduce achieves reliability through re-execution and simple atomic file operations. In addition to fault tolerance, MapReduce includes several optimizations that make it efficient at large scale. First, it uses locality optimization, meaning the master tries to schedule map tasks close to the input data. So most reads happen locally instead of over the network. Second, it uses fine-grained tasks, which improves load balancing. Faster machines can process more tasks, and slow machines do not delay the entire job. Third, it uses backup tasks to handle stragglers. Near the end of the job, The system launches duplicate copies of the slow remaining tasks and accepts the one that finishes first. Finally, MapReduce supports a combiner function which performs partial aggregation on the map side and reduces the amount of data that must be shuffled over the network. Now I will explain MapReduce using the classic word count example. The input text is first split into multiple pieces, and each piece is processed by a different map worker. During the map stage, the program emits intermediate pairs of the form word, 1 for every word it sees. Then, during the shuffle stage, the framework groups all pairs with the same word together. Finally, in the reducer stage, each reducer sums the list of the ones for a word and outputs the final count. This example clearly shows the purpose of MapReduce. The program writes simple logic while the framework automatically performs parallel execution and data grouping across the cluster. The paper evaluates MapReduce on a Google cluster of about 1,800 machines. Two key benchmarks are reported. For a 1 terabyte distributed grep job, the completion time is about 150 seconds. For a 1 terabyte distributed sort job, the completion time is about 891 seconds. The results also show that backup tasks are important. Without them, the sort job becomes 44% slower due to strangler tasks. Finally, when 200 workers were intentionally killed during execution, the job is still completed with only about a 5% slowdown, demonstrating strong fault tolerance. To conclude, MapReduce is important because it makes large-scale data processing much simpler. It allows programmers to write only two functions, map and reduce, while the framework handles parallel execution, scheduling, and communication. It also provides strong fault tolerance through automatic re-execution and improves performance using locality, combiners, and backup tasks. Overall, MapReduce became the foundation for many layer big data systems, including Hadoop. Thanks you for watching.